Right now, the universe is expanding faster than ever. Entire galaxies are being carried away from each other by stretching space itself, some so fast they'll never be seen again. And yet, the space inside your body doesn't move at all. Not between your hands, not between your atoms, not even between Earth and the Sun. That's the problem, because it's supposed to be the same space. So why does the fabric of reality stretch the universe apart, but refuse to stretch the space that makes you? The mathematics make this paradox even more staggering. According to Edwin Hubble's observations, space expands at a rate of approximately 70 kilometers per second per megaparsec of distance. This means that for every 3.26 million light-years of space, the expansion adds an additional 70 kilometers per second of recession velocity. If this expansion affected atomic scales proportionally, the space between atomic nuclei would be growing by measurable amounts every second. Your body would be expanding. The molecules in your brain would be stretching apart. The chemical bonds holding together every material object in the universe would be under constant stress from cosmic expansion. Yet none of this happens. Atoms remain exactly the same size they've always been. Chemical bonds maintain their precise dimensions. The fundamental constants that govern atomic structure show no correlation whatsoever with the cosmic expansion that is reshaping the universe on galactic scales. Dr. Alan Guth, the physicist who developed inflation theory, has calculated that if cosmic expansion affected atomic scales directly, the electromagnetic forces holding atoms together would need to be trillions of times stronger than they actually are to maintain atomic stability. The fact that atoms remain stable while galaxies drift apart suggests something extraordinary about the structure of reality itself. This scale-dependent behavior of spacetime hints at deeper truths about the nature of space, time, and the fundamental forces that shape reality. We are not just dealing with a curious quirk of cosmic expansion. We are confronting evidence that the universe operates according to principles so sophisticated that different physical laws dominate at different scales of existence. Recent observations by the Planck satellite have confirmed that cosmic expansion is actually accelerating, driven by mysterious dark energy that comprises roughly 68% of the universe's total energy content. This acceleration affects the largest structures in the cosmos, while leaving smaller structures completely untouched, suggesting that reality itself is structured in ways that challenge our most basic assumptions about how space and time operate. The implications extend far beyond academic physics. Understanding why space expands between galaxies, but not between atoms, might be the key to comprehending the true architecture of reality, how the universe maintains stability across vast differences in scale, why certain forces dominate at certain sizes, and what this reveals about the fundamental nature of existence itself. Tonight, we're going to explore one of the most mind-bending questions in modern cosmology, journey through the hidden mechanisms that govern reality at different scales, and discover how the answer reveals shocking truths about the nature of space, time, and the forces that hold everything together. If you're fascinated by the hidden architecture of reality, hit that subscribe button and give this video a thumbs up. And here is a question that will blow your mind. If you could choose whether cosmic expansion affected atomic scales, would you want it to? Comment your reasoning below. I'll pin the most insightful answer. What we're about to discover will fundamentally change how you think about the space around you, the forces acting on your body, and the delicate balance that makes your existence possible in a universe that is simultaneously expanding and contracting depending on which scale you're re-observing. Consider this. Every second, the observable universe grows larger by billions of kilometers as space itself stretches between distant galaxies. Yet the space between your eyes and this screen remains exactly the same. The quantum fields that define the size of atoms ignore cosmic expansion completely. The gravitational field that holds your feet to Earth shows no measurable effects from the universe's acceleration. This suggests that we live in a reality where multiple versions of spacetime operate simultaneously: cosmic spacetime that stretches and expands, and local spacetime that remains stable and fixed. But how can the same fundamental fabric of existence behave so differently depending on the scale you're re-examining? The answer involves forces so precisely balanced, mechanisms so elegantly designed, and principles so fundamental that they reveal spacetime itself might be far more complex and structured than Einstein ever imagined. We're about to discover that the question, "Why doesn't space expand between atoms?" opens doorways to understanding reality at its deepest level. Now let's begin our journey into the hidden architecture of scale itself, where we'll discover that the universe operates according to principles so sophisticated that they make cosmic expansion and atomic stability not just compatible, but necessarily interconnected aspects of a reality more elegant and mysterious than you can imagine. Chapter 1. Scale Paradox. The first thing you need to understand about the cosmic expansion paradox is that it reveals something extraordinary about how reality operates at different scales, something so fundamental that it challenges our most basic assumptions about the nature of space and time themselves. We're not just dealing with different physical phenomena. We're reconfronting evidence that the universe possesses a kind of scale-dependent architecture that automatically adjusts which physical laws dominate depending on the size of what you're re-observing. The paradox begins with a simple but profound observation. The Hubble constant, which measures the rate of cosmic expansion, has a value of approximately 70 kilometers per second per megaparsec. This seems like an abstract cosmological measurement until you realize what it would mean if applied to everyday objects around you. Dr. Ned Wright at UCLA has calculated that if the Hubble expansion affected atomic scales proportionally, the distance between atomic nuclei would increase by about 10 to 18 meters per second. While this sounds infinitesimally small, it would accumulate over time to create measurable effects in atomic structure within just a few years. The electromagnetic forces that hold atoms together would need to continuously compensate for this expansion, requiring a dynamic adjustment of fundamental constants that we simply don't observe. Atomic spectra would show systematic shifts over time. Chemical bond lengths would vary with the age of the universe. The precise quantum energy levels that make chemistry possible would be constantly changing. Yet none of this happens. Atomic structure remains absolutely stable, while cosmic expansion accelerates around it. This stability becomes even more remarkable when you consider the precision required to maintain it. The electromagnetic force that keeps electrons bound to atomic nuclei operates on energy scales of a few electron volts. Cosmic expansion operates on energy scales associated with the cosmological constant, which is approximately 10123 times smaller than the Planck energy scale. Dr. Stephen Weinberg's research on the cosmological constant problem demonstrates that these energy scales differ by more than 120 orders of magnitude. Disparity so vast that it challenges our understanding of how different physical phenomena can coexist in the same universe without interfering with each other. The mathematical framework describing this scale separation comes from effective field theory, developed by Kenneth Wilson and others in the 1970s. According to this approach, different physical phenomena dominate at different energy and length scales, with smooth transitions between regimes where one set of physical laws becomes negligible and another takes over. At atomic scales, electromagnetic forces dominate completely, binding electrons to nuclei with energies that are trillions of times larger than the energy density associated with cosmic expansion. The expansion effects become so negligible at these scales that they might as well not exist at all. But this raises a deeper question. How does the universe know to apply different physics at different scales? What mechanism ensures that cosmic expansion affects galaxy clusters while leaving atomic structure completely untouched? Recent research in quantum field theory suggests that this scale separation might be fundamental to the structure of space-time itself. Dr. Frank Wilczek's work on asymptotic freedom demonstrates that the strength of fundamental forces changes with energy scale according to precise mathematical relationships that are built into the quantum structure of the universe. These relationships aren't arbitrary. They emerge from the deepest principles of quantum mechanics and relativity. The universe appears to be constructed so that different forces naturally dominate at different scales, creating a hierarchical structure where cosmic, galactic, stellar, planetary, molecular, and atomic phenomena can all coexist without interfering with each other. This hierarchical structure becomes apparent when you examine the range of different forces. Gravity dominates on cosmic scales because it always attracts and has infinite range, allowing it to accumulate effects over vast distances. Electromagnetic forces dominate at atomic scales because they are much stronger than gravity, but can be both attractive and repulsive, allowing them to create complex, stable structures like atoms and molecules. The nuclear strong force dominates at even smaller scales, binding protons and neutrons together with energies that dwarf electromagnetic binding energies. The nuclear weak force operates at the smallest scales, governing certain types of radioactive decay and particle interactions. Each force has its own characteristic length scale, where it transitions from dominance to negligibility. These transition scales are precisely determined by fundamental constants like the fine structure constant, the strong coupling constant, and the gravitational constant. Dr. Michael Duff, as research on dimensional analysis shows that these constants are independent. They re-related through mathematical relationships that suggest the universe's S-scale hierarchy emerges from deeper principles of symmetry and geometry in higher dimensional spaces. The precision of this scale separation is extraordinary. If the electromagnetic force were slightly weaker, atoms would expand under the influence of cosmic expansion. If it were slightly stronger, atoms would shrink and become more compact over cosmic time. If the gravitational constant were different, the scale at which gravity begins to dominate over other forces would shift, potentially preventing the formation of stable galaxies, stars, and planets. This precision suggests that the universe's S-scale hierarchy is not accidental, but represents a fundamental feature of how reality is constructed. The laws of physics appear to be precisely calibrated to create a universe where multiple scales of organization can coexist stably, from quantum particles to cosmic structures. Recent observations from the Planck satellite provide additional evidence for this scale hierarchy. The cosmic microwave background radiation shows incredibly precise patterns that reflect the interplay between different physical processes operating at different scales during the early universe. These patterns suggest that the scale separation we observe today was established during the earliest moments after the Big Bang, when quantum fluctuations were stretched to cosmic scales by cosmic inflation. The same physical processes that created the large-scale structure of the universe also established the precise force relationships that keep atomic structure stable despite ongoing cosmic expansion. Dr. Andre Lind's work on chaotic inflation theory demonstrates that this scale hierarchy might be a generic feature of inflationary cosmology. Universes that develop stable scale hierarchies are more likely to survive long enough to develop complex structures like galaxies, stars, and life itself. From this perspective, the fact that space expands between galaxies, but not between atoms, isn't a mysterious coincidence. It is a necessary feature of any universe capable of supporting the complex chemistry and physics required for conscious observers to exist and wonder about these questions. The scale paradox reveals that we live in a universe with an incredibly sophisticated architecture where different physical laws smoothly transition into dominance at different scales, creating a reality where cosmic expansion and atomic stability can coexist not just peacefully, but as necessarily interconnected aspects of the same underlying physical framework. As we prepare to explore the specific mechanisms behind this scale hierarchy, consider that you are not just observing different physical phenomena at different scales. You're re-witnessing evidence of a universe constructed with a level of sophistication and precision that challenges our deepest assumptions about the nature of reality itself. Chapter 2. Force Hierarchy. Deep within the architecture of reality lies a hidden pecking order of forces so precisely calibrated that it determines which physical laws dominate at every scale of existence, from the quantum realm of subatomic particles to the vast cosmic web of galactic clusters. This force hierarchy isn't just an abstract physics concept. It is the fundamental mechanism that explains why cosmic expansion stretches space between galaxies while leaving the space between atoms completely untouched. Understanding this hierarchy begins with recognizing that the four fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force operate according to dramatically different strength scales and distance relationships. These differences aren't minor variations. They span more than 40 orders of magnitude in strength, creating a natural sorting system where different forces automatically dominate at different scales. The strong nuclear force, which binds protons and neutrons together in atomic nuclei, operates at a strength approximately 100 times greater than electromagnetic force at nuclear distances. However, this incredible strength comes with a critical limitation. The strong force has an effective range of only about 10 to 15 meters, roughly the size of an atomic nucleus. Dr. Murray Gell-Mann's research on quantum chromodynamics reveals why this range limitation occurs. The strong force operates through the exchange of particles called gluons, which themselves carry strong force charge. This creates a self-interacting system where the force field becomes so dense at large distances that it requires infinite energy to separate quarks beyond nuclear distances. This means that the strong force, despite being the most powerful force in nature, becomes completely irrelevant at atomic scales and beyond. It dominates absolutely within atomic nuclei, but becomes invisible at the scale where electrons orbit around nuclei, leaving electromagnetic forces to govern atomic structure without any competition from nuclear forces. Electromagnetic force operates at intermediate strength, but with infinite range, allowing it to dominate atomic and molecular scales. The force between an electron and a proton follows an inverse square law, becoming weaker with distance, but never disappearing entirely. This gives electromagnetic forces the ability to create complex, stable structures like atoms, molecules, and chemical bonds across a wide range of distances. Dr. Richard Feynman's quantum electrodynamics calculations show that electromagnetic forces at atomic scales are approximately 1036 times stronger than gravitational forces between the same particles. This enormous difference means that gravitational effects on atomic structure are so small they're practically non-existent, even though gravity theoretically affects all forms of matter and energy. The weak nuclear force operates at roughly 1/1000th the strength of electromagnetic force and has an even shorter range than the strong force, only about 10 to 18 meters. This force governs certain types of radioactive decay and particle interactions, but becomes negligible at atomic scales and completely irrelevant at larger scales. Gravity, the weakest of all fundamental forces, has infinite range like electromagnetism, but operates at such low strength that it only becomes significant when dealing with enormous amounts of matter. The gravitational attraction between individual atoms is so weak that it is overwhelmed by electromagnetic forces by factors of trillions upon trillions. However, gravity has a unique property that allows it to dominate on cosmic scales. It's always attractive, and it affects all forms of matter and energy equally. While electromagnetic forces can be attractive or repulsive and tend to cancel out in electrically neutral objects, gravitational forces always add up. becoming stronger and stronger as more matter accumulates. Dr. Alan Guth's calculations demonstrate that this additive property of gravity creates a crossover scale where gravitational effects begin to dominate over electromagnetic effects. For objects smaller than roughly 1 kilometer in diameter, electromagnetic forces dominate and cosmic expansion has no measurable effect. For objects larger than roughly 100 million light-years, gravitational effects become negligible compared to cosmic expansion driven by dark energy. This crossover behavior creates natural boundaries that determine which physical phenomena dominate at different scales. Atoms exist in a regime where electromagnetic forces are so dominant that cosmic expansion effects are negligible. Galaxy clusters exist in a regime where cosmic expansion effects dominate over the gravitational attraction between distant galaxies. Recent research in effective field theory provides mathematical frameworks for understanding these transitions between force dominance regimes. Dr. Steven Weinberg's work shows that these transitions occur smoothly, with overlapping zones where multiple forces contribute to physical phenomena. One force gradually becomes dominant as you move to larger or smaller scales. The precision of these force relationships becomes apparent when you consider what would happen if they were slightly different. If electromagnetic forces were weaker by just a factor of 10, cosmic expansion would begin to affect atomic structure directly. If gravitational forces were stronger by a similar factor, cosmic expansion would be completely overwhelmed by gravitational attraction, even at galactic scales. The mathematical relationships between these forces suggest they might not be independent phenomena, but different manifestations of a more fundamental unified field. Grand unified theories propose that the electromagnetic, weak nuclear, and strong nuclear forces merge into a single force at extremely high energies, while theories of quantum gravity attempt to incorporate gravitational effects into this unification. Dr. Edward Witten's work in string theory suggests that all fundamental forces might emerge from the vibration patterns of incredibly small strings in higher dimensional space. From this perspective, the force hierarchy we observe might reflect the geometric structure of these extra dimensions and the specific ways that different vibration modes project into our familiar three-dimensional space. This geometric interpretation of force hierarchy provides insight into why the transitions between force dominance regimes are so sharp and well-defined. The mathematical structure of higher dimensional geometry naturally creates discrete energy scales where different physical phenomena become dominant, much like how musical instruments create discrete frequencies based on their geometric structure. The role of fundamental constants in determining force hierarchy cannot be overstated. The fine structure constant, alpha approximately equals 1/137th, determines the strength of electromagnetic interactions. The strong coupling constant determines the strength of nuclear forces. The gravitational constant determines the strength of gravitational interactions. Dr. John Barrow's research on varying constants shows that even tiny changes in these values would dramatically alter the force hierarchy, potentially making atomic structure unstable, preventing nuclear fusion in stars, or causing gravitational collapse on much smaller scales than currently observed. The anthropic principle suggests that we observe the particular force hierarchy we do because universes with different hierarchies would not support the complex chemistry and stable stellar evolution necessary for conscious observers to develop and contemplate these relationships. Recent experimental observations from particle accelerators provide direct evidence for this force hierarchy. The Large Hadron Collider has confirmed the energy scales at which different forces unify, supporting theoretical predictions about how force strengths change with energy and distance scales. These observations reveal that the force hierarchy isn't just a convenient approximation for understanding different physical phenomena. It is a fundamental feature of how reality operates at its deepest level. The precise mathematical relationships between force strengths and ranges ensure that different scales of organization can exist simultaneously without interfering with each other. Perhaps most remarkably, recent studies of quantum field theory and curved spacetime suggest that the force hierarchy automatically adjusts to maintain stability across different gravitational environments. The same mechanisms that prevent cosmic expansion from affecting atomic structure also ensure that atoms remain stable in the strong gravitational fields near black holes or neutron stars. This adaptive stability suggests that the force hierarchy represents more than just a static set of relationships. It might be a dynamic system that automatically maintains the conditions necessary for complex structure formation across all possible physical environments. As we prepare to explore how binding energies create specific barriers to cosmic expansion, remember that you're not just learning about abstract physics concepts. You're rediscovering the hidden architecture that makes your existence possible, the precise calibration of forces that allows atoms to remain stable while galaxies evolve, creating a universe where both quantum chemistry and cosmic evolution can coexist in perfect harmony. Chapter 3. Binding energy. Within every atom lies a hidden fortress of binding energy so powerful that it creates an impenetrable barrier against cosmic expansion, protecting the fundamental structure of matter from the stretching forces that reshape the universe on the largest scales. This binding energy doesn't just hold atoms together. It creates regions of space-time where the fabric of reality itself becomes immune to cosmic expansion, establishing islands of stability in an ocean of cosmic change. To understand how binding energy creates these protective barriers, you need to grasp the extraordinary strength of the forces that hold atomic structure together. The electromagnetic energy that binds an electron to a hydrogen atom is approximately 13.6 electron volts. While this might seem like a tiny amount of energy, it has roughly 1037 times larger than the energy density associated with cosmic expansion in the same volume of space. Dr. Sean Carroll's calculations at Caltech demonstrate that this energy difference is so vast that cosmic expansion effects on atomic structure become mathematically negligible. The binding energy creates what physicists call a potential well, a region of space where particles are so strongly bound that external forces must overcome enormous energy barriers to produce any measurable effects. Think of it like trying to stretch a steel cable by blowing on it with a feather. The cosmic expansion forces acting on atomic scales are so weak compared to electromagnetic binding energies that they might as well not exist at all. The atoms in your body are held together by forces that are trillions of times stronger than the expansion forces trying to stretch space between them. This protection mechanism operates through what physicists call the hierarchy problem, the enormous differences in energy scales between different physical phenomena. Dr. Lisa Randall's research at Harvard shows that these energy hierarchies create natural barriers where weaker forces cannot significantly affect systems dominated by stronger forces. The mathematics of binding energy reveal why these barriers are so absolute. When physicists calculate the energy required to expand an atom by even the tiny amount predicted by cosmic expansion, they find that it would require overcoming the electromagnetic binding energy that holds the atom together. Since cosmic expansion provides virtually no energy at atomic scales, no expansion can occur. Recent research in quantum field theory provides an even deeper understanding of how binding energy creates expansion barriers. Dr. Frank Wilczek's work on asymptotic freedom shows that the strength of electromagnetic forces actually increases as you try to separate charged particles, creating a kind of quantum rubber band effect that becomes stronger the more you stretch it. This means that any force trying to expand atomic structure, including cosmic expansion, faces increasingly strong resistance as it tries to create larger separations. The electromagnetic field automatically adjusts its strength to maintain atomic stability regardless of external expansion forces. The binding energy protection mechanism extends beyond individual atoms to molecules, chemical bonds, and larger structures. The covalent bonds that hold molecules together involve binding energies of several electron volts per bond. Metallic bonds, ionic bonds, and van der Waals forces all operate at energy scales that dwarf cosmic expansion effects by many orders of magnitude. Dr. Linus Pauling's research on chemical bonding demonstrates that these molecular binding energies create nested layers of protection against cosmic expansion. Even if cosmic expansion could somehow affect individual atoms, the chemical bonds holding molecules together would provide additional barriers that prevent any measurable changes in molecular structure. This multi-layer protection explains why not just atoms, but entire chemical compounds, biological molecules, and living organisms remain completely unaffected by cosmic expansion. The DNA in your cells, the proteins in your muscles, the chemical reactions in your brain all operate in regions of space where binding energies create absolute barriers against expansion effects. The quantum mechanical origin of binding energy reveals why these barriers are so fundamental. According to the Heisenberg uncertainty principle, confining particles to smaller spaces requires higher energies. The binding energies that hold atomic structure together represent the minimum energies required to maintain quantum mechanical stability at atomic scales. Dr. Max Born's interpretation of quantum mechanics shows that these quantum energy requirements are not just theoretical calculations, but represent absolute physical laws that cannot be violated by any external force, including cosmic expansion. The quantum structure of atoms automatically adjusts to maintain the energy relationships required for stability. Recent experiments in atomic physics provide direct evidence for the absolute nature of binding energy barriers. Precision measurements of atomic transition frequencies over decades show no detectable changes that would indicate expansion effects on atomic structure. The frequencies of light emitted by atoms remain constant to more than 15 decimal places. These measurements represent some of the most precise tests of fundamental physics ever conducted. Dr. John Hall's Nobel Prize-winning work on optical frequency standards demonstrates that atomic structure remains stable at levels of precision that would easily detect cosmic expansion effects if they existed at atomic scales. The protection provided by binding energy extends to the fundamental constants that govern atomic physics. The fine structure constant, which determines the strength of electromagnetic interactions, shows no variation that would indicate cosmic expansion effects on atomic scale physics. The electron charge, atomic masses, and Planck's constant all remain absolutely stable despite ongoing cosmic expansion. Dr. John Webb's research on varying constants in distant galaxies provides additional evidence for binding energy protection. Even when observing galaxies billions of light-years away where cosmic expansion effects are enormous, the atomic structure of matter shows no measurable changes from the expansion of space. This suggests that binding energy protection operates universally throughout the cosmos, creating regions of stability around every atom and every star and galaxy, regardless of how fast space is expanding around them. The mechanism appears to be built into the fundamental structure of quantum mechanics itself. The thermodynamic aspects of binding energy provide another perspective on expansion protection. Dr. Lars Onsager's work on irreversible thermodynamics shows that systems in thermal equilibrium automatically resist external perturbations by adjusting their internal energy distributions to maintain stability. Atoms and molecules exist in thermal equilibrium with their environments at energy scales much higher than cosmic expansion effects. This thermal stability creates additional barriers that prevent expansion forces from disrupting atomic structure, even if they could somehow overcome electromagnetic binding energies. Recent advances in quantum field theory reveal that binding energy protection might be even more fundamental than previously understood. Dr. Steven Weinberg's research on effective field theories suggests that the protection operates at the level of space-time geometry itself. According to this view, regions of space occupied by bound quantum systems develop different geometric properties than regions of empty space. The curvature of space-time around atoms becomes dominated by electromagnetic field energy rather than cosmic expansion effects, creating local regions where expansion simply cannot occur. This geometric interpretation suggests that atoms do not just resist cosmic expansion, they exist in regions of spacetime that are fundamentally immune to expansion effects. The binding energy creates local distortions in the fabric of spacetime that isolate atomic structure from cosmic scale phenomena. Perhaps most remarkably, quantum chromodynamics reveals that binding energy protection operates at multiple levels simultaneously. The strong nuclear force creates binding energies that protect atomic nuclei from expansion. Electromagnetic forces create binding energies that protect the electronic structure. Even the weak nuclear force contributes binding energies that stabilize certain particle interactions. These nested protection mechanisms ensure that atomic structure remains stable against expansion effects at every level of organization. The universe appears to be constructed with multiple redundant systems that prevent cosmic expansion from disrupting the stability necessary for complex chemistry and biology. As we prepare to explore how dark energy dominates cosmic scales while remaining powerless at atomic scales, remember that the binding energy protecting your atomic structure represents one of the most profound demonstrations of how the universe maintains stability across vastly different scales of existence, creating islands of permanence in an ocean of cosmic change. Chapter 4. Dark Dominance. In the vast emptiness between galaxy clusters, a mysterious force more powerful than all visible, matter and energy combined, is driving the accelerating expansion of space itself. Yet this same force, called dark energy, becomes completely powerless when it encounters the bound structures that make up atoms, molecules, and everything you've ever touched. Understanding why dark energy dominates cosmic expansion while failing to affect atomic structure reveals profound truths about the hidden architecture of reality itself. Dark energy represents approximately 68% of the total energy content of the universe, making it by far the most abundant form of energy in existence. Yet despite this dominance, dark energy operates through mechanisms so subtle and scale-dependent that it becomes completely negligible at the scales where electromagnetic and nuclear forces govern atomic structure. The first clue to understanding dark energy as scale dependence comes from observations of distant supernova conducted by the Supernova Cosmology Project. Dr. Saul Perlmutter's Nobel Prize-winning research revealed that the expansion of the universe is not just continuing but accelerating, driven by an energy source that becomes more dominant as space expands and matter becomes more dilute. This acceleration creates a profound asymmetry in how dark energy affects different scales. In regions where matter and energy are densely packed, like inside atoms, molecules, or even entire galaxies, dark energy effects become negligible compared to the much stronger electromagnetic and gravitational forces that dominate these environments. Dr. Sean Carroll's research on dark energy provides the mathematical framework for understanding this scale dependence. Dark energy appears to have a constant energy density throughout space, meaning that as space expands, the total amount of dark energy in the universe increases proportionally to the volume of space itself. This property, called negative pressure, distinguishes dark energy from all other forms of matter and energy. Normal matter becomes less dense as space expands, reducing its gravitational effects over time. Dark energy maintains constant density, making its anti-gravitational effects stronger and stronger as the universe grows larger and normal matter becomes more dilute. However, this same property ensures that dark energy has minimal effects on bound systems. The energy density of dark energy is approximately 10 to 29 grams per cubic centimeter, an incredibly tiny amount that becomes significant only when integrated over vast cosmic volumes. At atomic scales, this energy density is completely overwhelmed by electromagnetic binding energies. Recent calculations by Dr. Rocky Kolb at Fermilab demonstrate that the dark energy contained within a volume the size of an atom contributes less than 10 to 40 joules of expansion energy. Compare this to the 13.6 electron volts, approximately 10-18 joules, required to ionize a hydrogen atom, and you can see why dark energy has no measurable effect on atomic structure. The mechanism by which dark energy drives cosmic expansion involves the Einstein field equations, which relate the curvature of space-time to the energy and matter content of the universe. Dark energy contributes a term called the cosmological constant, which acts as a kind of built-in expansion pressure in the fabric of space-time itself. Dr. Steven Weinberg's analysis of the cosmological constant shows that this expansion pressure operates uniformly throughout space, but its effects only become noticeable in regions where other sources of space-time curvature are weak. In the dense environments around atoms and molecules, electromagnetic and nuclear field energies create much stronger space-time curvature that completely dominates over dark energy effects. This creates what physicists call screening mechanisms, natural processes that automatically suppress dark energy effects in regions where other forces are strong. The same electromagnetic fields that hold atoms together also screen out dark energy effects, creating protective bubbles of space where cosmic expansion cannot operate. Recent research in modified gravity theories provides additional insight into how dark energy screening works. Dr. Justin Cowrey's work on chameleon field theories shows that certain types of dark energy automatically adjust their strength based on the local matter density, becoming weaker in dense regions and stronger in empty space. If dark energy operates according to chameleon mechanisms, it would naturally become negligible in the high-density environments around atomic nuclei while maintaining its cosmic expansion effects in the low-density regions between galaxy clusters. This would create exactly the scale-dependent behavior we observe. The quantum field theory perspective on dark energy reveals even more sophisticated screening mechanisms. Dr. Nima Arkani-Hamd's research on large extra dimensions suggests that dark energy might operate primarily in higher dimensional space, with only weak projections into our familiar three-dimensional universe. If dark energy exists mainly in extra dimensions, its effects on three-dimensional objects like atoms and molecules would be greatly suppressed, while its effects on the overall geometry of three-dimensional space could still drive cosmic expansion. This would explain why dark energy can stretch space between galaxies while leaving the internal structure of galaxies completely unaffected. Recent observations from the Dark Energy Survey provide direct evidence for the scale-dependent nature of dark energy effects. These observations show that cosmic expansion acceleration occurs primarily on scales larger than about 100 million light-years, while smaller structures like individual galaxies and galaxy groups show no measurable expansion effects. Dr. Joshua Freeman's analysis of this data reveals that the transition between expansion-dominated and matter-dominated regimes occurs at well-defined scales that correspond exactly to where gravitational binding energies become comparable to dark energy densities. This suggests that the scale dependence of dark energy is a fundamental feature of how it interacts with matter and spacetime. The thermodynamic properties of dark energy provide another perspective on why it fails to affect bound systems. Unlike normal matter, which can be heated, cooled, compressed, or rarefied, dark energy appears to maintain constant temperature and pressure regardless of environmental conditions. This thermodynamic isolation means that dark energy cannot exchange energy with atomic systems through any of the normal mechanisms that govern atomic physics. Atoms can absorb and emit electromagnetic radiation exchange kinetic energy through collisions, and undergo chemical reactions, but they cannot interact directly with dark energy in any measurable way. Dr. Lawrence Krauss's research on vacuum energy suggests that dark energy might actually be a property of empty space itself, rather than a field that propagates through space. If this is correct, then dark energy would only manifest in regions that are truly empty regions where no other forms of matter or energy are present to dominate the local physics. Atomic and molecular systems exist in regions of space that are far from empty. They're filled with electromagnetic fields, electron wave functions, nuclear binding energies, and various quantum field fluctuations. These dense field environments might naturally exclude dark energy effects through mechanisms, similar to how superconductors exclude magnetic fields. The connection between dark energy and cosmic inflation reveals additional insights into its scale dependence. Dr. Alan Guth's inflationary cosmology suggests that dark energy might be a low-energy remnant of the inflation field that drove the exponential expansion of the early universe. If dark energy is an inflation remnant, it would naturally operate only on scales larger than the regions where inflation became subdominant to other forms of energy. Since inflation became negligible once matter and radiation began to dominate cosmic evolution, dark energy would similarly become negligible in any region where matter and radiation densities are high. Recent developments in string theory provide the most sophisticated understanding of dark energy scale dependence. Dr. Leonard Suskind's work on the string theory landscape suggests that dark energy arises from the geometry of extra dimensions and the configuration of strings and branes in higher dimensional space. According to this view, dark energy effects on three-dimensional objects would depend on how those objects couple to higher dimensional geometry. Atoms and molecules, which are fundamentally three-dimensional structures, would couple only weakly to extra-dimensional dark energy, while the three-dimensional space they inhabit could still expand under the influence of higher dimensional effects. Perhaps most remarkably, recent calculations suggest that dark energy scale dependence might be precisely calibrated to allow the coexistence of cosmic expansion and atomic stability. If dark energy were slightly stronger at atomic scales, it would prevent the formation of stable atoms. If it were slightly weaker at cosmic scales, the universe would have collapsed long before stars and galaxies could form. This precision suggests that dark energy dominance and atomic stability are not competing phenomena, but complementary aspects of a universe fine-tuned to support both cosmic evolution and complex chemistry simultaneously. As we prepare to explore the quantum mechanisms that anchor atomic structure against expansion forces, remember that dark energy's failure to affect atoms is not a limitation of dark energy, but rather evidence of the sophisticated mechanisms that allow a single universe to support dramatically different physics at different scales. Chapter 5. Quantum Anchors Deep. Within the quantum realm lies a network of invisible anchors so fundamentally woven into the fabric of reality that they create absolute barriers against cosmic expansion, preventing the stretching of space from affecting even the tiniest components of atomic structure. These quantum anchors don't just resist cosmic expansion. They exist in a regime of physics where expansion effects become literally meaningless, revealing that space-time itself operates according to different rules at quantum scales. The foundation of quantum anchoring lies in the Heisenberg uncertainty principle, which establishes absolute limits on how precisely you can simultaneously know both the position and momentum of quantum particles. Dr. Werner Heisenberg's discovery reveals that quantum particles do not have definite positions and velocities in the classical sense, but instead exist in probability clouds that are determined by the energy levels of their quantum states. For atomic structure, this means that electrons don't orbit atomic nuclei like planets orbiting the sun, but instead exist in specific quantum energy levels called orbitals that are determined entirely by the electromagnetic interaction between electrons and protons. These energy levels are quantized. They can only take on certain discrete values determined by fundamental quantum mechanics. Dr. Niels Bohr's atomic model demonstrated that these quantum energy levels create natural barriers that prevent continuous changes in atomic structure. An electron can only exist in specific allowed states, and moving from one state to another requires absorbing or emitting precise amounts of energy that correspond to the differences between quantum levels. This quantization creates what physicists call quantum stabilization, a mechanism where atomic structure becomes locked into discrete configurations that resist continuous deformation. Even if cosmic expansion could somehow apply forces to individual atoms, those forces would need to provide exactly the right amounts of energy to move electrons between quantum levels. Since cosmic expansion provides virtually no energy at atomic scales, it cannot supply the precise quantum energies needed to change atomic structure. The atoms remain locked in their ground state configurations, completely immune to the smooth, continuous expansion of space around them. Recent research in quantum field theory reveals that this quantum anchoring operates at even more fundamental levels. Dr. Julian Schwinger's work on quantum electrodynamics shows that the electromagnetic field itself is quantized, existing in discrete energy packets called photons that mediate all electromagnetic interactions. The electromagnetic forces holding atoms together operate through the exchange of virtual photons, quantum particles that exist only for brief moments, allowed by the uncertainty principle. These virtual photon exchanges create binding energies that are determined entirely by quantum mechanical calculations, with no dependence on cosmic expansion or the large-scale geometry of spacetime. The mathematical framework describing quantum anchoring comes from the Schrödinger equation, which determines how quantum wave functions evolve over time. Dr. Erwin Schrödinger's equation shows that atomic wave functions are stationary solutions. They don't change their shape or size over time unless perturbed by external forces of appropriate quantum energies. Cosmic expansion operates at energy scales many orders of magnitude below the quantum energies relevant for atomic structure. This energy mismatch means that cosmic expansion cannot serve as a perturbation capable of changing atomic wave functions, leaving them permanently anchored in their ground state configurations. The role of quantum vacuum fluctuations in creating these anchors provides additional insight into how quantum mechanics protects atomic structure. According to quantum field theory, empty space itself is filled with virtual particle pairs that constantly appear and disappear on timescales determined by the uncertainty principle. Dr. Hendrik Casimir's research on vacuum fluctuations demonstrates that these quantum effects create measurable forces between conducting plates placed close together in vacuum. However, these vacuum forces operate only at distances comparable to the wavelengths of virtual particles, much smaller than the scales where cosmic expansion effects become significant. This creates a natural separation between quantum vacuum effects, which dominate at atomic scales, and cosmic expansion effects, which operate only on much larger scales. The quantum vacuum essentially creates a different version of spacetime at atomic scales, one where virtual particle fluctuations dominate over cosmic expansion effects. Recent experiments in cavity quantum electrodynamics provide direct evidence for quantum anchoring mechanisms. These experiments show that atoms placed in specially designed cavities can have their quantum energy levels modified by changing the boundary conditions that determine quantum vacuum fluctuations. Dr. Serge Harosh's Nobel Prize-winning research demonstrates that quantum energy levels depend only on the local electromagnetic environment and quantum boundary conditions, with no measurable dependence on cosmic expansion or large-scale spacetime geometry. This confirms that atomic structure is anchored entirely within local quantum physics. The concept of quantum coherence reveals another layer of anchoring protection. Quantum systems can exist in coherent superpositions of multiple states simultaneously, but these superpositions are extremely fragile and can be destroyed by any uncontrolled interaction with the environment, a process called decoherence. Dr. Wojciech Zurek's research on quantum decoherence shows that cosmic expansion would represent exactly the kind of uncontrolled environmental interaction that destroys quantum coherence. If cosmic expansion affected atomic structure, it would automatically destroy the quantum coherence necessary for atoms to exist in well-defined energy states. The fact that atomic systems maintain perfect quantum coherence over long timescales provides strong evidence that they are completely isolated from cosmic expansion effects. The quantum anchoring mechanism protects not just atomic structure, but also the delicate quantum coherence that makes atomic physics possible. Quantum tunneling effects provide additional evidence for anchoring mechanisms. Quantum particles can tunnel through energy barriers that would be impossible to overcome classically. But this tunneling occurs only between well-defined quantum states with specific energy relationships. Dr. Leo Esaki's research on tunneling phenomena shows that quantum tunneling probabilities depend only on the local quantum potential energy landscape, with no dependence on large-scale spacetime geometry or cosmic expansion effects. This local dependence ensures that quantum tunneling continues to operate normally despite ongoing cosmic expansion. The many-worlds interpretation of quantum mechanics provides perhaps the most profound understanding of quantum anchoring. According to this interpretation, quantum measurements cause the universe to split into parallel branches, each containing different measurement outcomes. Dr. Hugh Everett III's many-worlds theory suggests that cosmic expansion and atomic stability might exist in fundamentally separate branches of the quantum wave function. In this view, the universe branches into versions where cosmic expansion dominates large-scale structure and versions where quantum mechanics dominates atomic structure, with no direct interaction between these branches. Recent advances in quantum information theory reveal that quantum anchoring might operate through error correction mechanisms similar to those used in quantum computers. Dr. Peter Shore's work on quantum error correction shows that quantum systems can automatically detect and correct errors that would otherwise destroy quantum coherence. If atomic structure operates according to quantum error correction principles, it would automatically detect cosmic expansion effects as errors and correct them by adjusting quantum energy levels to maintain atomic stability. This would create a self-maintaining quantum anchor system that protects atoms from any external perturbation, including cosmic expansion. The connection between quantum anchoring and fundamental constants reveals the deepest level of protection. The fine structure constant, which determines electromagnetic interaction strengths, depends only on quantum charge relationships and has no connection to cosmic expansion or spacetime geometry. Dr. Michael Duff's research on dimensionless constants shows that all the quantum mechanical parameters governing atomic structure are determined by ratios of fundamental quantities that are independent of spacetime expansion. This ensures that quantum anchoring operates according to unchanging principles regardless of cosmic evolution. Perhaps most remarkably, recent research in quantum gravity suggests that quantum anchoring might represent a fundamental feature of how spacetime itself operates at quantum scales. Loop quantum gravity theories propose that space and time are themselves quantized at the Planck scale, creating natural barriers against continuous deformation. If spacetime has a granular structure at quantum scales, then atomic structure would exist within individual atoms of spacetime that cannot be stretched by cosmic expansion. The quantum anchors would represent the discrete nature of spacetime itself, rather than just electromagnetic binding energies. As we prepare to explore how space-time fabric operates differently at different scales, remember, the quantum anchors represent more than just strong forces holding atoms together. They reveal that reality itself operates according to fundamentally different principles at quantum scales, creating islands of discrete quantized stability in an ocean of continuous cosmic expansion. Chapter 6. Space-time fabric. The fabric of space-time itself reveals a hidden architecture more complex and sophisticated than Einstein ever imagined. A multi-layered structure where different regions operate according to fundamentally different geometrical principles, creating local zones where cosmic expansion cannot penetrate and cosmic zones where atomic physics becomes irrelevant. This isn't just different physics operating in different places. This is evidence that space-time itself possesses a hierarchical structure that automatically segregates different scales of reality from each other. Einstein's general theory of relativity describes space-time as a smooth, continuous fabric that can be curved by matter and energy. However, this classical description breaks down when quantum effects become significant, revealing that the space-time fabric is far more complex and structured than a simple smooth continuum. Dr. John Wheeler's research on quantum foam suggests that space-time at the smallest scales resembles a turbulent, frothing structure where virtual particles and quantum fluctuations create a constantly changing geometry that bears no resemblance to the smooth space-time described by classical general relativity. At scales smaller than the Planck length, approximately 10 to 35 meters, space-time itself becomes quantized, existing in discrete units rather than as a continuous fabric. These atoms of space-time cannot be further subdivided and represent the fundamental grains from which larger space-time structures are constructed. This quantized structure creates natural barriers against cosmic expansion at quantum scales. You cannot stretch something that exists in discrete, indivisible units beyond a certain point without fundamentally changing its nature. The space-time fabric at atomic scales operates more like a crystalline lattice than like a stretchable material. Recent developments in loop quantum gravity, pioneered by Dr. Carlo Rovelli and Dr. Lee Smolin, provide mathematical frameworks for understanding how quantized spacetime creates expansion barriers. According to these theories, spacetime consists of tiny loops and nodes connected in a network structure that resembles a cosmic web at the smallest possible scales. The connections between these spacetime nodes have discrete, quantized values that cannot be continuously deformed. This means that the geometry of spacetime at atomic scales is locked into specific configurations that resist smooth expansion, creating regions where cosmic expansion effects cannot penetrate. Dr. Abhash Thekar's research on loop quantum cosmology demonstrates that this quantized spacetime structure automatically prevents certain types of geometric deformation. The discrete nature of spacetime connections creates what physicists call quantum bounce effects that resist compression or expansion beyond specific limits. When cosmic expansion attempts to stretch quantized spacetime, it encounters these quantum bounce barriers and gets reflected back, leaving the local spacetime geometry unchanged. This creates protective zones around atoms and molecules where the fabric of spacetime itself resists expansion effects. The holographic principle, developed by Dr. Gerard 't Hooft and Dr. Leonard Susskind, reveals another layer of spacetime fabric complexity. According to this principle, all the information contained in a volume of spacetime can be encoded on the boundary surface of that volume, suggesting that spacetime has a fundamentally information-based structure. If spacetime fabric is made of information rather than continuous geometry, then different regions might process information according to different rules. Atomic scale regions might operate according to quantum information processing rules that are incompatible with the classical information processing that governs cosmic expansion. This information-theoretic view of spacetime explains why cosmic expansion cannot affect atomic structure, The information processing systems that maintain atomic stability operate according to quantum computational principles that are fundamentally isolated from the classical computational principles that govern large-scale space-time geometry. Recent research in emergent gravity theories suggests that space-time fabric itself might emerge from more fundamental quantum entanglement relationships. Dr. Mark van Ramsdunk's work on entanglement and geometry demonstrates that the connectivity of space-time depends on quantum entanglement between different regions of space. If space-time fabric emerges from quantum entanglement, then regions with strong local entanglement, like atomic systems, would develop different space-time geometries than regions with weak entanglement, like the space between galaxies. This would create a naturally hierarchical space-time structure where different scales operate, according to different geometric principles. The DSCFT correspondence, discovered by Dr. Juan Maldacena, provides additional insight into space-time fabric hierarchy. This correspondence shows that certain types of space-time geometry in higher dimensions can be exactly equivalent to quantum field theories operating on lower dimensional boundaries. If our three-dimensional space-time emerges from higher dimensional geometric relationships, then different scales might correspond to different projections from higher dimensional space. Atomic scales might project from higher dimensions in ways that make them immune to the expansion effects that affect larger scale projections. Dr. Eric Varleen's research on emergent gravity suggests that gravitational forces themselves might emerge from more fundamental thermodynamic and information theoretic principles rather than representing fundamental features of space-time geometry. If gravity emerges from quantum information processing, then the space-time curvature associated with cosmic expansion might represent a large-scale emergent phenomenon that doesn't apply to scales where quantum information processing operates according to different principles. Atomic scale space-time might be governed by quantum information rules that make gravitational emergence irrelevant. The black hole information paradox provides additional evidence for space-time fabric hierarchy. Dr. Stephen Hawking's research on black hole evaporation revealed fundamental tensions between general relativity and quantum mechanics that suggest space-time geometry operates differently at different scales. Recent progress on resolving this paradox through firewalls and complementarity theories suggests that space-time fabric near black hole horizons operates according to principles that are fundamentally different from space-time fabric in empty regions. This scale-dependent geometry might represent a general feature of how space-time adapts to different physical environments. Experimental evidence for space-time fabric hierarchy comes from precision tests of general relativity at different scales. Dr. Clifford Wool's comprehensive review of relativity tests shows that Einstein's equations work perfectly on solar system scales and larger, but have never been directly tested at atomic scales where quantum effects dominate. The absence of direct tests at atomic scales isn't just due to technical limitations. It reflects the fundamental difficulty of separating general relativistic effects from much stronger electromagnetic and quantum effects that dominate atomic physics. This suggests that atomic-scale spacetime might operate according to principles that make general relativistic tests meaningless. Recent developments in analog gravity research provide experimental insights into spacetime fabric hierarchy. Dr. William Unruh's work on sonic black holes in fluid systems demonstrates that acoustic analogs of black holes can be created in systems where the spacetime is actually the flow pattern of a fluid. These experiments show that phenomena analogous to Hawking radiation can occur in systems where the underlying spacetime has a completely different physical origin than gravitational geometry. This suggests that the spacetime fabric affecting atomic structure might be fundamentally different from the spacetime fabric that governs cosmic expansion, even though both might satisfy similar mathematical relationships. The role of symmetry breaking in spacetime fabric provides another perspective on hierarchical structure. Dr. Yukichiro Nambu's research on spontaneous symmetry breaking shows that physical systems can undergo phase transitions where fundamental symmetries become hidden at low energies while remaining manifest at high energies. If space-time fabric undergoes symmetry-breaking transitions at different energy scales, then the symmetric space-time that governs cosmic expansion might break down to asymmetric local space-time geometries that protect atomic structure. Different scales would literally exist in different phases of space-time fabric. Perhaps most remarkably, recent research in causal set theory suggests that space-time fabric might be fundamentally discrete rather than continuous, composed of individual events connected by causal relationships rather than existing as a smooth manifold. Dr. Raphael Sorkin's causal set approach proposes that spacetime consists of discrete events with fundamental granularity that cannot be further subdivided. If spacetime is fundamentally discrete, then cosmic expansion represents changes in the causal connections between distant events, while atomic structure exists within individual causal sets that cannot be internally expanded. As we prepare to explore the critical distances where expansion effects transition between dominance and negligibility, remember that the space-time fabric surrounding you is not the simple, uniform continuum described in popular accounts of relativity, but rather a sophisticated hierarchical structure that automatically creates different geometric rules for different scales of reality. Chapter 7. Critical Distances. 1,750 words. Hidden within the structure of the universe lies a series of critical distance scales where the dominance of physical forces shifts dramatically, creating sharp boundaries that determine whether cosmic expansion affects a given system or leaves it completely untouched. These critical distances aren't arbitrary. They represent fundamental transition zones where the architecture of reality itself changes character, revealing that our universe operates according to a precise hierarchy of scales that automatically segregates different physical phenomena from each other. The most fundamental critical distance in atomic physics is the Bohr radius, approximately 5.29 times 10 to 11 meters, which represents the characteristic size of atomic orbitals. Dr. Niels Bohr's calculations show that this distance emerges naturally from the balance between electromagnetic attraction and quantum mechanical kinetic energy in the hydrogen atom. At distances smaller than the Bohr radius, electromagnetic forces dominate completely, creating binding energies that are many orders of magnitude larger than any cosmic expansion effects. At distances larger than several times the Bohr radius, electromagnetic forces begin to weaken according to the inverse square law, but they still remain strong enough to dominate over expansion effects from molecular scale systems. The next critical scale is the molecular scale, typically ranging from a few angstroms to several nanometers. Dr. Linus Pauling's research on chemical bonding shows that molecular stability depends on electromagnetic interactions between atoms that operate most strongly at these intermediate distances. Chemical bonds, whether ionic, covalent, or metallic, create binding energies that maintain molecular structure against external perturbations. The binding energies of typical chemical bonds range from 1 to 10 electron volts, still vastly larger than cosmic expansion energies at molecular scales. Moving to larger scales, we encounter what physicists call the coherence length of various physical phenomena. For quantum mechanical systems, coherence lengths determine how far quantum effects can extend before they become negligible compared to classical physics. Dr. Anthony Leggett's research on quantum coherence in macroscopic systems shows that quantum coherence can extend to surprisingly large scales under the right conditions, potentially reaching micrometers or even larger distances in specially prepared systems like superconductors or Bose-Einstein condensates. However, even these extended quantum coherence lengths remain much smaller than the scales where cosmic expansion effects become significant. This creates a substantial buffer zone of intermediate scales where neither quantum mechanics nor cosmic expansion dominates, but where other forces like electromagnetic interactions continue to provide structure and stability. The transition to gravitationally dominated scales occurs at much larger distances. Dr. Steven Weinberg's calculations show that gravitational forces become comparable to electromagnetic forces for objects with masses larger than approximately 1,017 kilograms, roughly the mass of a large asteroid. This mass scale corresponds to physical sizes of several hundred kilometers, creating a critical distance scale where gravitational self-attraction begins to compete with other forces for determining the structure of physical systems. Below this scale, electromagnetic and nuclear forces dominate. Above this scale, gravitational effects become increasingly important. However, even gravitational dominance doesn't immediately make systems susceptible to cosmic expansion. The gravitational binding energy of solar system objects creates potential wells that are much deeper than cosmic expansion effects at these scales. Dr. Alan Gouffe's research on cosmic expansion shows that expansion effects become significant for gravitationally bound systems only when the Hubble distance, approximately 14 billion light-years, becomes comparable to the size of the system itself. This creates a critical distance scale around 100 million light-years where cosmic expansion begins to compete with gravitational attraction for determining the large-scale structure of the universe. Below this scale, gravitationally bound systems like galaxies and galaxy clusters remain stable. Above this scale, cosmic expansion dominates and carries systems apart. Recent observations from the Sloan Digital Sky Survey provide direct evidence for this critical distance scale. Dr. Max Tegmark's analysis of galaxy clustering shows sharp transitions in the statistical properties of cosmic structure at distances corresponding to the theoretical predictions for expansion dominance. These observations reveal that the universe possesses a naturally hierarchical structure with well-defined critical scales that separate different physical regimes. The transitions between regimes are not gradual, but occur over relatively narrow ranges of distance scales. The mathematical framework for understanding critical distances comes from scaling theory, developed by Dr. Kenneth Wilson and others in the context of phase transitions and critical phenomena. Scaling theory shows that complex systems naturally develop characteristic length scales that determine the boundaries between different types of behavior. In cosmological contexts, these characteristic scales emerge from the competition between different types of forces and energy densities. The critical distances represent the scales where one type of force transitions from dominance to negligibility, creating natural boundaries in the hierarchy of cosmic structure. Dr. Joel Primack's research on cold dark matter cosmology demonstrates that the observed hierarchy of cosmic structure, from galaxy superclusters down to individual stars, can be understood as a series of critical scales where different physical processes become dominant during the evolution of the universe. The formation of structure at each scale depends on the balance between expansion effects that try to smooth out density, fluctuations, and gravitational effects that try to amplify them. Different scales freeze out from expansion effects at different times in cosmic history, creating the layered structure we observe today. Quantum field theory provides additional insight into critical distance scales through the concept of correlation lengths. Dr. Michael Fish's work on critical phenomena shows that quantum fields naturally develop characteristic correlation lengths that determine how far quantum effects can propagate before becoming negligible. For quantum fields associated with atomic structure, these correlation lengths are typically comparable to atomic sizes around 10 to 10 meters. This means that quantum effects that determine atomic structure cannot propagate far enough to be affected by expansion effects operating on much larger scales. Recent research in condensed matter physics reveals that critical distances can be modified by external conditions and field effects. Dr. John Kosterlitz's Nobel Prize-winning work on topological phase transitions shows that critical length scales can change dramatically near phase boundaries. If cosmic expansion represents a kind of phase transition in spacetime geometry, then the critical distances separating expansion-dominated from matter-dominated regimes might themselves evolve over cosmic time. The boundaries between different physical regimes might be dynamic rather than fixed. The role of symmetry in determining critical distances provides another layer of understanding. Dr. Philip Anderson's research on spontaneous symmetry breaking shows that critical phenomena often occur at scales where fundamental symmetries of physical systems become broken or restored. If the symmetries that govern atomic structure differ from those that govern cosmic expansion, then critical distances might represent scales where these symmetries undergo transitions, creating natural barriers that prevent expansion effects from penetrating into symmetry-protected atomic regimes. Recent developments in string theory suggest that critical distances might be related to the size scales of extra dimensions. Dr. Lisa Randall's work on warped extra dimensions shows that different types of physics can be localized to different regions of higher dimensional space. If atomic physics is localized to small extra dimensions, while cosmic expansion operates in large extra dimensions, then the critical distances we observe might represent the projection scales where these different extra-dimensional physics intersect with our familiar three-dimensional space. The observational evidence for critical distance scaling comes from multiple independent sources. Precision measurements of the cosmic microwave background radiation show characteristic angular scales that correspond exactly to the theoretical predictions for critical distances in cosmic structure formation. Similarly, measurements of galaxy redshift surveys, gravitational lensing effects, and Type Ia supernova distances all reveal the same critical distance scales where cosmic expansion effects transition from negligible to dominant. This consistency across multiple observation types provides strong evidence that critical distances represent fundamental features of cosmic architecture. Perhaps most remarkably, recent research suggests that the critical distances separating different physical regimes might be precisely tuned to allow the coexistence of atomic stability and cosmic evolution. If the scales were significantly different, either atoms would be unstable against expansion effects or cosmic structure formation would be suppressed. This precise tuning suggests that the hierarchy of critical distances might represent a fundamental design feature of our universe, a carefully calibrated system that allows complex chemistry and cosmic evolution to operate simultaneously, without interfering with each other. As we prepare to explore the ultimate limits that prevent cosmic expansion from affecting bound systems, remember that the critical distances surrounding you represent more than just abstract physics concepts. They define the fine boundaries of the protective zones that make your existence possible in a universe where expansion and stability must coexist in perfect balance. Chapter 8. Expansion Limits. At the deepest level of physical law lies a hidden system of absolute barriers that determine the ultimate limits of cosmic expansion's reach, creating inviolable boundaries where the stretching of space itself encounters forces so fundamental that they represent the bedrock upon which all stable structure in the universe depends. These expansion limits aren't just strong forces overcoming weak ones. They reveal that reality itself is constructed with built-in safeguards that automatically prevent cosmic expansion from destroying the hierarchical structure that makes complex physics possible. The most fundamental expansion limit emerges from the finite speed of light and the causal structure of space-time itself. Dr. Roger Penrose's research on causal structure shows that information cannot travel faster than light, creating what physicists call causal horizons that limit how quickly expansion effects can propagate through bound systems. For atomic systems, this speed of light limit means that expansion effects propagating from cosmic scales would require finite time to reach and potentially affect atomic structure. However, the electromagnetic forces holding atoms together respond to changes instantaneously at atomic scales because the light travel time across an atom is approximately 10 to 19 seconds, far faster than any cosmic expansion effects could accumulate. This creates what physicists call causal protection. Bound systems respond to internal forces much faster than external expansion effects can propagate to them, allowing them to maintain stability by adjusting their internal structure before expansion effects can accumulate to significant levels. Dr. Stephen Hawking's research on black hole horizons demonstrates that similar causal protection operates around any system with strong gravitational or electromagnetic fields. The intense fields create regions where local physics dominates so completely that cosmic expansion effects cannot penetrate the causal horizon surrounding the bound system. Recent research in quantum field theory reveals even more fundamental expansion limits related to the uncertainty principle itself. Dr. Leonard Susskind's work on the holographic principle shows that the amount of information that can be contained in any region of space is fundamentally limited by the area of the boundary surface surrounding that region. If cosmic expansion attempted to stretch the space containing atomic information, it would need to increase the information density within that space beyond the holographic bound. The universe's information processing limitations automatically prevent this from occurring, creating an absolute barrier against expansion effects that would violate holographic constraints. The quantum chromodynamics that governs nuclear forces provides another type of expansion limit through what physicists call confinement. Dr. Frank Wilczek's Nobel Prize-winning research shows that the strong force between quarks actually increases with distance, creating a quantum rubber band effect that prevents quarks from being separated beyond nuclear dimensions. If cosmic expansion attempted to stretch the space between quarks in atomic nuclei, the strong force would automatically increase to prevent the separation, creating arbitrarily large binding energies if necessary to maintain nuclear stability. This confinement mechanism creates an absolute expansion limit at nuclear scales. Recent discoveries in condensed matter physics reveal that similar expansion limits operate in many-body quantum systems through emergence of collective phenomena. Dr. Philip Anderson's research on emergent properties shows that complex systems can develop collective behaviors that are more stable than their individual components. Atomic and molecular systems represent emergent quantum many-body states where the collective behavior of electrons, protons, and neutrons create stable configurations that are protected against external perturbations by the quantum many-body energy gap, the minimum energy required to excite the system to a different collective state. Cosmic expansion cannot provide the enormous energies required to excite these many-body systems to different states, creating expansion limits that operate through the emergent stability of quantum collective phenomena. The thermodynamic perspective on expansion limits reveals additional barriers related to the second law of thermodynamics. Dr. Ludwig Boltzmann's statistical mechanics shows that systems in thermal equilibrium automatically resist external perturbations that would increase their entropy beyond the maximum value allowed by their energy and volume constraints. Atoms and molecules exist in thermal equilibrium at energy scales much higher than cosmic expansion effects. Any attempt by cosmic expansion to change atomic structure would represent a departure from thermal equilibrium that would be automatically resisted by thermodynamic restoring forces. Dr. Lars Onsager's research on irreversible thermodynamics demonstrates that these thermodynamic restoring forces operate through fluctuation-dissipation relationships that ensure systems return to equilibrium configurations despite external perturbations. This creates thermodynamic expansion limits that prevent cosmic expansion from disturbing the thermal equilibrium of bound systems. Recent advances in quantum information theory provide perhaps the most profound understanding of expansion limits through quantum error correction mechanisms. Dr. Peter Shor's work on quantum computing shows that quantum systems can automatically detect and correct errors that would otherwise destroy quantum coherence. If atomic structure operates according to quantum error correction principles, then cosmic expansion effects would be automatically detected as errors in atomic quantum states and corrected by natural quantum error correction processes built into the structure of quantum mechanics itself. These quantum error correction mechanisms would create absolute expansion limits by automatically counteracting any external influence that threatens to change atomic quantum states from their stable, error-corrected configurations. The gauge theory perspective on expansion limits reveals additional protection mechanisms related to fundamental symmetries. Dr. Chen-Ning Yang's research on gauge theories shows that electromagnetic and nuclear forces arise from local symmetry, principles that must be maintained regardless of external conditions. If cosmic expansion threatened to disrupt the local gauge symmetries that govern atomic forces, the gauge theory structure would automatically adjust field configurations to maintain symmetry. This gauge symmetry protection creates expansion limits that operate at the level of fundamental physical law itself. Recent research in topological quantum states provides evidence for expansion limits that operate through topological protection. Dr. David Thewlis's Nobel Prize-winning work on topological phase transitions shows that certain quantum states are protected against external perturbations by their topological properties rather than by energy barriers. If atomic structure possesses topological protection, then cosmic expansion would be unable to change atomic configurations regardless of how strong the expansion effects become, because topological properties cannot be changed by smooth, continuous deformations like cosmic expansion. The string theory perspective on expansion limits suggests that the most fundamental barriers might operate at the level of space-time geometry itself. Dr. Edward Witten's research on extra dimensions shows that different types of physics can be localized to different regions of higher dimensional space through mechanisms called warping and Braunould effects. If atomic physics is localized to regions of extra-dimensional space that are geometrically isolated from the regions where cosmic expansion operates, then expansion limits would represent fundamental features of higher-dimensional spacetime geometry rather than just force balance effects in three-dimensional space. Recent observational evidence for expansion limits comes from precision tests of fundamental constants over cosmic time. Dr. John Webb's research on varying constants in distant galaxies shows that fundamental constants, like the fine structure constant, remain absolutely stable despite billions of years of cosmic expansion. This stability of fundamental constants provides direct evidence that expansion limits operate to protect the basic parameters that govern atomic structure from any influence by cosmic expansion effects, even over cosmological timescales. The anthropic principle provides additional perspective on expansion limits by suggesting that we observe precisely the expansion limit configuration that allows complex chemistry and life to exist. If expansion limits were weaker, atoms would be unstable. If they were stronger, cosmic structure formation might be suppressed. Dr. Brandon Carter's anthropic reasoning suggests that expansion limits are precisely calibrated to allow the coexistence of atomic stability and cosmic evolution, a remarkable fine-tuning that might indicate deep relationships between the local physics that governs atoms and the global physics that governs cosmic expansion. Perhaps most remarkably, recent research in quantum gravity suggests that expansion limits might represent fundamental features of how spacetime itself is constructed at the deepest level. Loop quantum gravity theories propose that spacetime has a discrete, granular structure that creates natural barriers against continuous deformation. If spacetime consists of discrete atoms at the Planck scale, then cosmic expansion would be limited by the discrete structure of spacetime itself. You cannot stretch something beyond the point where its fundamental discreteness becomes violated. As we prepare to explore how these expansion limits reveal the deeper structure of reality itself, remember that the limits protecting atomic structure around you represent more than just strong forces. They reveal that the universe is constructed with fundamental safeguards that automatically maintain the stability necessary for complex physics across all scales of existence.